Welcome to this lecture series in real analysis. In this lecture, we'll define the Euler's constant and prove that it is irrational. And all we need to know is the description of the exponential function in terms of its infinite series as written over here. Okay. So what is Euler's constant? Euler's constant is this number x of 1, which is nothing but the sum of this infinite series. So that's Euler's constant. We also write it as E. That's a standard notation in the honor of the great mathematician Leonhard Euler. All right, so the first thing we will do is prove this inequalities. So we are saying that you can approximate the Euler's constant very well with respect to this rational number. So put more precisely, this rational number is very close to the Euler's constant. And the larger you choose the n, the better the estimate. And this is a very simple exercise. In fact, I could leave this as an exercise, but let me do the details. So we have E by definition equals the sum, which we write in two parts. Correct? So we will take the first part to the left side and we have this equation. Right? So clearly this is therefore positive because this is positive. So this part of the inequality has been proven. So let's prove this. And yeah, before I go on, I should have written for all natural numbers n. Anyway, that was anyway clear. So we need to estimate this. And let me write this as summation r from 1 to infinity, 1 upon, sorry, what have I written? Yeah, so this is correct. So this is 1 upon n plus r factorial, right? But this is less than equal to 1 upon n factorial times 1 upon n plus 1 to the power r. So all I'm saying is that, in fact, this is strictly less than. So what I'm saying is that this term is strictly less than that. Let's see why. So for example, if r were equal to 1, then all we are saying is this factorial is less than, well, for r equals to 1, we can say only this much because the two things are actually equal. But for r equals 2, what we have is, so here they are actually equal, but for r equals 2, we have n plus 2 factorial, which is 1 upon n factorial times 1 upon n plus 1 factorial, n plus 1 times 1 upon n plus 2. But this is strictly less than 1 upon n plus 1. Right? And these two things product out to give us the square that we see here and so on. So I'm sure now you see this strict inequality. The first term for r equals to 1, the two terms are equal. But after that, you have a strict inequality. So you can write a strict inequality here. And now this is nothing but 1 upon n factorial summation of this geometric series, which I leave as an exercise to check is nothing but 1 upon n. So this geometric series is nothing but 1 upon n, and hence this is strictly less than that number. Right? So it was a very simple calculation, but I did it in full. Okay, so we have this, and now let's make one remark as to Suppose we wanted to calculate the value of E to some precision, we can use this, right? If you choose n as, let's say, 10, then you know that this number, which is a rational number, we can explicitly compute it using a calculator, is very close to the Euler's constant, because this is a very small number when n is equal to 10. So even for n is equal to 10, you get a very, very precise approximation for the Euler's constant. And you'll see it will look like 2.71 something, something, something. You can Google. So anyway, I have written a very modest version of that over here, that the Euler's constant is between 2 and 3. But as I said, it is something like 2.71 something, something, something. Anyway, but the main point of today's lecture is to show that the Euler's constant is irrational, and it has a very interesting proof. Okay, so we'll show that E is irrational, and the proof we will give is due to Joseph Fourier. All right, so we just saw an estimate that 0. Yeah, so before we say anything, suppose E is rational. We'll proceed by contradiction. Suppose E is rational and say it is equal to P by Q, where P and Q are positive integers. Since E is assumed to be rational, and since we already know E is positive, we can write it as the ratio of two positive integers. All right, and now we know that E minus this number, this is a positive number, and strictly less than 1 upon Q times 1 upon Q factorial. This is what we proved, right? And now here is the idea. If we multiply this thing with Q factorial, we will get an integer. Why? Because instead of E, let's write P by Q, because we have assumed that E is equal to P by Q, right? So the thing is, if you multiply this guy with Q factorial, you get an integer, because this will be an integer and that will be an integer. But on the right side, we will see 1 over Q. So we'll end up saying that we have a positive integer. Because of this part, we have a positive integer strictly less than 1 over Q, which is, of course, at most 1. Q is, after all, a positive integer, so this is at most 1, and that will be a contradiction. So let me do the details. So let me just multiply both sides by Q factorial. Correct? We can write this. So this says that 0 is less than, I'll write this as capital N, or let me write that as capital Q, is less than 1 upon Q. So this whole thing I'm saying is capital Q, where we know capital Q is an integer, and a positive integer at that. So it's a natural number. It is an integer because this is an integer and that is an integer, and difference of two integers is an integer, but it is also positive, so it is a positive integer. Right, so we are saying that we have a positive integer Q which is situated between 0 and 1, because 1 upon Q is at most 1, right? If Q is equal to 1, this is exactly equal to 1, but otherwise it is at most 1. I mean, one can always say that this is at most 1. So Q is strictly less than something that is at most 1, so Q would then be strictly less than 1. So we are saying that we have a positive integer Q situated between 0 and 1, but that is of course absurd. So this contradiction shows that the Euler's constant is irrational, and we are done. A very nice proof of the irrationality of the Euler's constant. And let me remark, or let me first pose a question. We have seen that E is irrational, but what about E squared? What about E squared? Is it irrational? What about E cubed? What about some power of E? What about some combination of them? Could it be so that this thing is rational? Maybe something like this might be rational. Is it possible? The answer is no. No matter what kind of expression you write here, there's a precise meaning to it. Whatever kind of expression you write here, where all these coefficients are rationals, and yeah, you have these powers and you sum it up, you will never get a rational number unless you choose all of them to be 0, of course. So that is called the transcendence or the transcendental nature of the Euler's constant. And I encourage you to Google about transcendental numbers and maybe read some articles which show you a proof of the fact that the Euler's constant is transcendental. It's not an easy proof. It's much more difficult than what we have here. A very short piece of reasoning won't suffice, probably. But I encourage you to read it. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.